An article here discusses French colonists who came to northeast Canada in the 17th and 18th centuries, establishing an agricultural settlement called Acadia in and around present-day Nova Scotia. I was going to do a video on this interesting story, their relationship with a Native American tribe called the Micmac, the land reclamation feat of turning salty marshland into highly productive agricultural land by building dikes and sluices called eboiteaux, the unique tidal properties of the Bay of Fundy, next to which they settled, and their experiences during and after the several French and British battles for control over this land. However, I never got that far, not even close. I was stuck in the 16th century, with the voyage of French explorer Jacques Cartier across the Atlantic in search of a western water route to Asia. Of minor interest to me about his voyage was that he sailed from a town called St. Malo, which featured prominently in a Pulitzer Prize-winning book called All the Light We Cannot See. Of major interest to me was that he sailed directly east to west and made the trip in 20 days. This was interesting because I'd read that the trade winds in that part of the Atlantic blew from west to east, and so I wondered how and why he traveled directly against the wind, and how he was able to make the trip so quickly, or at least what I thought was so quickly. This is where the research for this video got seriously sidetracked. In trying to answer this question, I went deeper and deeper down the rabbit hole. My first question was, what causes the trade winds? Researching this question led me to other questions, such as, what exactly are the trade winds and why do they form? Why and how does atmospheric air circulate? Why do hot air molecules rise? How do air molecules gain and lose energy? And how does that affect them rising and falling in the atmosphere? Each time I asked why, I went deeper and deeper into nested Wikipedia articles and beyond. But I quickly ran into a concept called the Coriolis Effect. Now this is where I need to apologize. I haven't spent weeks and months studying the answers to all these questions. I've spent 4 days, and I didn't start off with much knowledge about atmospheric science. So not only do I not have any definite answers, it's very possible my reasoning in this video might be plain wrong. But I wanted to make a video describing my understanding, since it might spark your interest in a related topic, or perhaps generate a comment pointing me in the right direction, so that I might make a more useful future video. Okay, the idea is that if you're on, say, a merry-go-round spinning counterclockwise, and you throw a ball toward the center, the ball will appear to you to curve to the right. This, it is said, is due to the Coriolis effect, sometimes called the Coriolis force. But the force isn't real. It's only an illusion based on the perspective of someone on the merry-go-round. What's happening is that the ball, at the instant it is thrown, has two velocity components. One is to the right, due to the rotational speed of the merry-go-round. The other is toward the center, due to the throw. Combining these two, the resulting velocity will be in a straight line at an angle, neglecting things like air resistance and gravity. But from the perspective of the person who threw the ball, he would expect the ball to continue going directly away from him even as he spins. This would produce a motion like this, but that's impossible because there would be no force acting on the ball to cause it to go in that direction. And so, from his perspective, the ball veers right off its expected path. And it's this apparent veering right that is caused by what's called the Coriolis effect, or Coriolis force. But it's not real. It really should be called the Coriolis illusion. Anyway, now if we create a three-dimensional merry-go-round, we get the northern hemisphere of the Earth. The same thing happens here. Rotational speed at the equator around the Earth's axis of rotation is about 1,000 miles per hour. If we fire a bullet, say, at 1,000 miles per hour directly north, its velocity will be a combination of these two velocities, and will travel at a 45-degree angle northeast. Again, we're neglecting gravity and air resistance, but looking top-down, this is the path it should take. Now, an interesting thing happens when we take into account gravity and the curvature of the Earth. If we fire that same bullet, now viewed from the side, and it goes so fast that gravity pulls it toward the Earth but it doesn't hit the ground, kind of like a satellite in orbit, the principle of conservation of angular momentum comes into play. Angular momentum is described by this equation, where m is the mass of the object, r is the distance from the axis of rotation, and v is the velocity around the axis of rotation. As the bullet gets pulled closer to the Earth's axis of rotation, its angular momentum will remain the same, which means its velocity around the circumference will increase because its distance from the axis decreases. So, for instance, if it goes to a point that is half the distance to the axis of rotation, its velocity will double to keep the momentum the same. This means that not only will the bullet travel to the right because of its initial velocity of 1,000 miles per hour, but it will actually increase speed to the right because of the conservation of angular momentum. The same thing happens if we change the direction of the bullet by firing it south from the North Pole. Initially, its velocity to the right would be very small, because the speed of rotation near the North Pole is very small. So the new velocity, which is a combination of the velocity to the right and the velocity in the direction it was fired, is nearly straight south. And if we fire it fast enough, it will continue south without hitting the ground, and its velocity to the right will decrease because of the conservation of angular momentum. As it gets further from the axis of rotation, its speed to the right will get smaller and smaller until it's going almost totally straight south. Now imagine the bullet is a molecule of air, which is impossible because there's no such thing as an air molecule. There's nitrogen gas, oxygen gas, water vapor, carbon dioxide, etc. But let's just say a molecule of air. Because of solar radiation and other things, there are currents of air in the atmosphere that circulate like this. I'll put links below to some videos I watched that explain this. In this circulation, as the air moves north, its rightward velocity increases due to conservation of angular momentum. And these are the trade winds here, the ones I thought would have made it hard for Cartier to travel directly from France to Canada. In this circulation, as the air moves south, its rightward velocity decreases, and this is what really got me sidetracked in my research. If it's true that due to conservation of angular momentum, its rightward velocity decreases relative to a frame of reference in outer space, then that would mean to an observer on the Earth near the equator, it would appear that there would be a wind blowing from the northeast. These are the trade winds that Columbus took to get to the Caribbean. If this is true, then I wonder if those winds are less an effect of them blowing over the surface of the Earth than the Earth spinning under the atmosphere, creating the effective wind. In the same way, when you skydive out of an airplane, you don't say it was windy because you recognize you were falling through the air, and not that the air was blowing upwards at you. Or if you put your hand out the window of a car, you don't think, wow, it's windy out, because you know you're traveling quickly through the air, and it's not that the wind is blowing toward the car. If that's the case, then is it true that the sails of ships traveling from Spain to the Caribbean are acting like parachutes, simply catching the slow-moving air as the ships rotate past on the surface of the Earth, allowing them to let the Earth rotate under them west to east, even though from their perspective they think they're being pushed by a wind traveling east to west? Or, to put this another way, imagine a baseball player standing on the equator throwing a baseball to the east at 100 miles per hour. Because he and the air and everything around him is traveling at 1,000 miles per hour relative to an observer in outer space, to him it looks like the ball is traveling 100 miles per hour away from him. But to the observer in space, the ball is traveling 1,100 miles per hour. But if he turns around and faces west and throws the ball, from his perspective the ball is traveling 100 miles per hour away from him to the west. But to the observer in space, the ball is still traveling to the right, but only at 900 miles per hour. Does that mean that the catcher, who is traveling with the Earth 1,000 miles per hour to the right, is simply catching up to the baseball, which is only going 900 miles per hour to the right? Now, I don't know if all this is painfully obvious to some, entirely irrelevant to everyone, or just plain wrong. I feel like to properly understand trade winds, I'd need to plumb the depths of physics, chemistry, planetary science, quantum mechanics, and everything in between, and I just don't have time for that. At the very least, hopefully this video has sparked your interest in asking why about something that might seem obvious at first, but upon closer inspection, might have a bit more nuance than you thought. Anyway, if you made it this far, and even if you haven't, have a great day.